Hey everyone, today we're going to finish up talking about part of polynomial functions. Yesterday we talked about zeros, the degree, the end behavior. Today we're going to talk about a few more characteristics and then we'll wrap up with actually doing a graph of a polynomial function. The first thing I want to talk about is the intermediate value theorem for polynomial functions. This is considered an existence theorem just because it's actually just letting you know that something exists given a certain set of conditions. It is something that you will do more extensively in calculus, but it's something that I think is important that you're introduced to now, so I did want to bring this up to you. The intermediate value theorem, sometimes referred to as the IVT, says this, and it sounds very wordy, but it actually is very straightforward. It says if f is a polynomial function with real coefficients and f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c is 0. So basically what that's saying is this, and you can see this on your note sheet. So if you didn't print out the note sheet yet, go ahead and stop the video and then print it out from the assignment page. But it's saying this, if f of a is right here and f of b is right here, I'm changing signs to get from f of a to f of b, right? F of a is negative, f of b is positive. So because it's a polynomial function, that means it's continuous. We talked about that yesterday as well. It's a nice smooth curve. Because it's continuous and they have opposite signs, somewhere between a and b, I have to cross the x-axis. Because one is negative and one is positive, I have to cross the x-axis, which means I have to have a 0 between the values of a and b. Okay, that's what the intermediate value theorem is saying. So let me show you an example of what that is. It says, given this polynomial function, show that it has a real 0 between 2 and 3. So I don't need to graph it. I don't need to look at it visually. All I need to do is figure out what f of 2 and f of 3 are equal to. So, if I go ahead and find f of 2, if I find f of 2, and I go ahead and plug that in, so I've got 2 cubed minus 2 times 2 minus 5. That gives me 8 minus 4 minus 5 gives me negative 1. And if I find f of 3, I end up with 3 cubed minus 2 times 3 minus 5. And that gives me 16. And because the sign changes, so the sign of f of 2 is negative 1, but the sign of f of 3 is positive, right? It comes out to be positive 16. Because the sign changes, that tells me by the IVT, or by the intermediate value theorem, that there is a 0, or a root is a 0 between 2 and 3. Pardon my bad handwriting there. Okay, that's all it says. It doesn't tell you what the 0 is. It just tells you that there exists a 0 between these two values, between 2 and 3. Okay, that's all that the IVT tells you. So that could be valuable when you're doing different kinds of graphs and looking at different things. It is something that I just feel is important to share with you, so I wanted to show that to you. Okay, another important thing to note is the whole idea of turning points. So a turning point is when a function changes from increasing to decreasing or decreasing to increasing. And the idea is this: whatever the degree of the polynomial is, the graph will have at most one less than that turning point. So let me show you what I mean. This graph in red down here is a 4th degree polynomial. That's y equals x to the 4th minus 8x squared. So 1 less than 4 would be 3. So at most it has 3 turning points, which in this case it does. It's a turning point there, it's got a turning point there, and it's got a turning point there. Okay, so it has 3 turning points. If you look at the blue one, this is a 5th degree polynomial, so that means it would have at most 4 turning points, which does 1, 2, 3, and 4. And the reason that that's important is that will help us when we're creating our graph and when we're sketching our graph out. Okay, so let's go ahead and try an example. The example we have here is graphing x to the 4th minus 2x squared plus 1. And I basically gave you a list of things that you need to make sure that you look for, or steps that you kind of have to go through when you are graphing. And I tried to write them as briefly as possible, but here's the idea. The first thing we want to do is determine the end behavior, and you can almost literally make a list of all the things that that we're going to be doing. So let's see, let's determine the end behavior. Okay, the degree is even, which means either both ends are up or both ends are down. And because my leading coefficient is positive, that means both ends are up. Okay, that's the first thing. The next thing I want to do is find the 0. So I'm going to set this equal to 0 to find my zeros. So set that equal to 0. Now this is, it's like a quadratic, but instead of x squared and x, it has x to the 4th and x squared. So when you're factoring it, you should recognize that and say, well, instead of having x and x, I'm going to have x squared and x squared. And now I need two numbers that add to -2 and multiply to +1. So it's going to be -1 and -1. Okay, so here my roots are x are plus or minus 1. Here my roots are also x are plus or minus 1. So +1 shows up twice, -1 shows up twice. So they both have a multiplicity of 2. That takes us to step 3. So what I like to do is this, just to make a mental note. Let me rewrite that. So x equals 1 has mult of 2, and x equals -1 has mult of 2. That just tells me the multiplicity. So I know that when I graph it, I have to bounce off the x-axis at 1 and at -1. Okay, the next thing we're going to do is find the y-intercept by computing f of 0. This is a pretty easy step. All you're doing is plugging in 0 wherever you see an x, right? So I have 0 to the 4th minus 2 times 0 squared plus 1. And that just gives me 1. So I know f of 0 is 1. Step 5 says to check for symmetry. This goes back to a while ago we did this. We talked about symmetry. We talked about even and odd symmetry. Basically, we're checking f of -x. And we plug that in. -x to the 4th minus 2 times -x squared plus 1, which gives us x to the 4th, right, minus 2x squared plus 1. So here's the deal, right? If I take a negative number and I raise it to an even power, it just becomes a positive number. So that's what happened in this particular problem, was that when I substitute -x in for x, I get back the same function that I started with. And because of that fact, it's an even function, which means it has y-axis symmetry. Y-axis symmetry. So that's going to help us when we're graphing it. And then number 6, I'm going to squeeze this in down here, determine the number of turning points. So Because this is a 4th degree polynomial, at most I could have 3 turning points. Now that doesn't guarantee that I absolutely have 3. I just know I can't have more than 3. Okay, so that's basically everything I need to sketch a graph. So when we say sketch a graph, we're not saying that everything is going to be exact in this graph. It's just giving us an idea of the general shape of it. When you get into calculus, you'll be doing curve sketching, so it'll be in much more detail, and you'll know exactly where the maxes and the mins are, and how to go about finding them. But for now, we're just really doing a rough sketch. So I know that I have a root at, or a 0 at +1 and -1. I know that my y-intercept is at +1, so I know I'm going to be crossing the y-axis at +1. I know that my end behavior is that my graph it goes up on the ends. I also know that my function has y-axis symmetry, so it's going to look the same on the left and on the right of the y-axis, and that at both roots I bounce off the x-axis. I don't cross the x-axis because of my multiplicity of 2. So based on that information, here's a sketch of what my graph is going to look like. So I'm going to get to my root, I'm going to bounce off. I'm going to get to my other root and bounce off. And there's your graph. And that's just a rough sketch of the graph. So that's the kind of work that I'm looking for when you're going through and doing these problems. It's like I said, none of these other points need to be exact. It's just a rough sketch. But your zeros and your y-intercept should be pretty accurate when you're doing it. If you're doing a graph, for example, that does something like this, you might not know where this high point or where this low point is, so I'm not looking for that information. You don't need to be exact with that. I just want the general shape of what the graph would be. So one of you might draw it like that, and somebody else might draw it like this, right, where it's more exaggerated. As long as you have the right roots and the right y-intercept and the correct end behavior, I'm not too concerned with where those maxes and minimum values are. Okay, so hopefully that helps. Hopefully this video will help you out with doing the assignment. And if you have any questions, let me know. Otherwise, I'll see you guys on Monday. All right, take care, everybody. Bye-bye.